Your audio is currently not connected.
Hi guys, can I get a sound check?
I can hear you.
Yep,
Okay,
you're good
great.
now.
Thanks. All right. Boy. So, let's see here. I think this is where we stopped last time, which was at the concept of design rules. So we talked about, all these steps that you go through to create the CMOS process. And so it's a function of, building this thing up layer by layer. And, some of the buildup happens early on in the process, and those are all things you're changing the silicon itself by changing the doping concentration, et cetera. And then there's the stuff that you actually layer onto the silicon, like the polysilicon gate and the capacitance, et cetera. Sorry about my dog, guys. She'll be going at it for a while. So basically, once you might go through 100, 150 different steps using 30 to 50 mask layers, or whatever the process has, and then you get this wafer. This is what the manufacturing plant is doing. So when you're designing a chip, let's see. So when you're designing a chip, like as circuit designers, what we're used to seeing are like schematics, right? So we have, a PMOS transistor or an NMOS transistor, or I don't know, a diode, or a bipolar. We won't deal with bipolar transistors in this class, or bipolar. So these are all schematic symbols we have, and we use these to simulate and spice and so on. But the manufacturer doesn't know what to do with a schematic. This has no meaning to the manufacturer. I mean, of course, they understand what it is as engineers, but they can't use that to do anything. So there's the wafer, that they built up through all these processes, and then there's the schematics. And so you have to go through this intermediate process, and this is what we do as designers, is to basically draw what these masks will look like. Okay, so like this, instead of let me just draw. So if you just had a NMOS transistor, it would kind of look like this. This would be a polygate. So actually, let me do this, just to give you guys a flavor here. Duplicate. No, I don't want to do that. Okay, let's do that. Okay, so let's say on one hand I had a NMOS that I wanted to, in the computer-aided design tool. So this is a computer-aided design tool, and it'd be like, I don't know, something like Spice. Cadence is something called Spectra, and so on. It's a bunch of like equation solvers that you plug this into and do simulations, etc. And then, what we want at the end is this wafer full of our design. And then we have to basically draw these masks also in our CAD tool. And let's say, and then we draw them layer by layer. For example, this NMOSFET, the first thing I would do is I would select the layer called active, and I would draw a rectangle. So this would be in layer called active. So this has a certain layer number that's agreed to by, I'm going to call layer 1, it might be called anything. That's the agreement between us and the foundry about what this layer means. Okay, what this layer does, the layer active, is it basically puts a hole in the, so remember we had this very thick silicon dioxide. That was the isolation between transistors. So this puts a hole in that silicon dioxide. So what this does is this basically you ended up having this thick silicon dioxide, and then this puts a hole where that is. Okay. And then next thing is I want to define the poly gate. Okay. So then I draw a poly gate. There's a reason I put this dog bone in here. And it's not just because my dog is barking. Okay, so by the way, over down here, I am drawing a cross section over here. Okay, so if I do that, you'll see that the poly kind of looks like this. Okay, and so that's the poly, and it has a certain layer number. Let's call it layer number 2. Can you guys still see my screen?
Yeah, you're good.
Okay, great. And then you know, the other nice thing this does, if you guys remember, this is a so-called self-aligned process, meaning that once the poly is defined, and we do implants, the implants automatic, because the poly is like a mask for the implants, and so is the thick silicon dioxide layer, by the way. So you end up with this, the implants sort of naturally happen with poly acting as the mask. So you basically, poly will also make these guys source and drains, okay, by nature. Okay, then I need to, so now I have kind of everything I need right here for a NMOS transistor. I have a gate, I have the source, I have the drain, but I need to connect to it because the chip is not just the transistors, but also the connection between the transistors. So what I do is I draw what's a layer called contact. And that'll have another layer number. And then I'll drop a contact there, I'll drop a contact here, I'll drop a contact here, because I want to connect to these 3 points. So if I just do the cross section here, because the contact for the poly is offset from this particular cross section, so if that cross section is the plane of my iPad or your screen, you can think of the contact with the poly is kind of closer to your face, so we don't really see it on this line of cross section. Does that make sense?
Wait, can you repeat that?
Sure. So I'm really sorry about my drawing, guys. Here, so you know, this is the top. This is the top drawing, right? The top view, and this is the side view. Okay, or the cross section. It's called the cross sectional view. And this is the top view. The thing is, the cross-sectional view, I have to decide, I have to draw a line through the top view to decide, you know, that's the cross section. So here I picked this line across here. Okay, so if I take that line across, I won't see the dog bone of the poly, and I won't see the poly contact, I'll see this part of the poly right here. And that's why I've just drawn this. Okay, if I draw another cross-sectional view, so I'm going to draw it to cross-sectional view 1, so I'm going to call this 1. Then I'm going to do cross-sectional view 2. So if I do that, then what will I see? Okay, so I'm going to see there's no, so let's say this section, this cross-sectional 2 goes through here, say. Okay. So when I look at that cross-sectional view, notice there is no active, right? There's no active here or here, which is the cross-sectional view. So it'll just be this thick oxide. Does that make sense, guys? We're going from the top view to the cross-sectional view. And so because in this cross-sectional view, too, there is no active, right? As I'm like going down that from across 2, say from 2 to 2 prime, right? I don't see any active there, right? Active is offset up here. So just a silicon dioxide isolation. But then I see the dog bone of my poly, which is wider than this poly. So it looks wider. And then I'll also see my contact. So I'll also see a contact drawn on that poly. Does that make sense, guys?
Yeah.
Yeah.
So it's like the N plus is like behind this cross sectional 2. Like if you're to
Yeah.
go like depth wise.
Exactly. So
Okay, I see
this guy's sort of closer to your face if you go this way. It's closer to your face, and then this guy is at the plane of the display.
Okay, yeah, that makes sense.
And also notice this guy, the poly here, is sitting higher than the poly here. So it's kind of like this. So the poly there, which is exactly this. The poly here, so this, if this was the contact, this part of the poly, it needs to be a dog. The reason it's a dog bone is because it needs to overlap or be bigger than the contact size. So you need to make it a little bit bigger so you get this nice, so this is poly here. So trying to pretend like this was my drawing, but notice this part of the poly is sitting on this thick oxide, whereas this part of the poly is sitting on a much thinner oxide. So you kind of get this step down type of thing as well. Okay. Where was it? Here. Okay, and then so going back to our original plane, so then we have, because we can see the contacts on the N plus, we'll get this contact here and a contact here. Okay, and then let's say I draw a metal 1, the first layer metal. So I'll draw it like this. And then a layer metal 1 here going this way for whatever reason. Okay, so if I again look down here, it'll look like I have metal 1. No, sorry. It look like I have metal 1 here and metal 1 here on cross-sectional view 2. Okay, but because I don't have any metal on the poly in this cross-sectional view 1, there won't show up any on the poly there. Okay, for the sake of discussion, let's say I had metal 1 here overlapping the poly. So in cross-sectional 2, I would see metal 1 on the poly there. Okay, but the main thing here is that this is what we would draw. This top view is what we draw in the CAD tool.
Professor, quick question.
Sure.
What's the purpose of the metal one?
So when you're just at the level of the transistor, so imagine you have your chip and you don't have any metals yet on the chip at all. So you have a bunch of NMOS and PMOS transistors. In fact, you might have billions of them on this chip of yours, right, that you designed. But they can't do anything by themselves. They're just sort of sitting there. Your complete circuit is combination of these transistors doing some functionality. For example, a CMOS inverter, which we'll talk about later today. So it's an inverter, right? So that looks like, a PMOS connecting to an NMOS with the NMOS source grounded and the PMOS source connected to a high voltage. So that's called VDD. Let's say that's whatever it is, depends on the process. Or a CMOS NAND gate looks like, we'll talk about these. Just take my word for it for now. Looks like, so these are high supply, ground. This is connected. How do I do this? Kind of like that. So the upshot is like these schematics are connections of these active devices. So the metal layers are what connects these transistors together. So, and the metal one is the first layer of these interconnections. And because, imagine if you just had, so does that make sense why you would have metal interconnections?
Yeah, I'm kind of getting it now.
Okay. And then the reason you have a bunch of metal interconnections is if you just had one layer of interconnection, if imagine trying to connect up a billion things with one layer, like pretty quickly you'd block yourself off. So what you do is you go, you basically jump between layers to sort of jumper across up and down to be able to make connections. Okay, so the more, because let's say if you had a metal 2 over a metal 1, there's a dielectric between them, so it could draw a metal 2 over a metal 1, then they wouldn't short with each other unless you put a contact layer down. Or a metal 3 wouldn't short with a metal 1 or whatever. So you can sort of, it's called escape routing, because like you won't, you're trying not to paint yourself into a corner or corner yourself. So it's called escape routing. The more metal you have, you can kind of jumper up and down the different metal layers and, go and connect to other things. So that's kind of the idea behind it. Does that make sense?
Yeah, thank you, Professor.
Sure.
So it's like three-dimensional wiring, sort of.
Exactly. So the CMOS process or a VLSI process is called a planar process, Planar, planar. And so what that means is all the active devices, so the transistors, diodes, whatever, are in a two-dimensional plane. So like you can't put an NMOS on top, physically on top of another NMOS. They're all on the same layer of the chip. But the interconnections are sort of in dimensions above that. So you can think of that as more like a three-dimensional connection of these metal layers with the dielectrics in between them connecting things up.
Okay.
And see if I don't know what happened to my drawing. Let's see. Let's just do this. Whoops. So CMOS cross. So there's a, you can actually, people actually do this. So what you do is, see CMOS cross section, scanning. SEM is a scanning electron microscope. Well, that wasn't helpful. Well, no, it's kind of helpful. Okay, so I just sort of, what? Which one of these is good? Let's go to this one. That's better. Okay, so this is an actual cross section. So what they did was they build up some chip, and they go through and they saw, and there's different ways to, you have to get this surface really smooth. So this is actually this drawing here. Whoops, this guy on the right here, guys. Oh, whoops. This guy is the actual cross section. Okay, and what you see here is you see the diffusions. Those will be the N plus P. You see the polysilicon, and then you see these contacts, and going to these metal layers, and then there's the different metal layers going up, so you can actually connect these. Okay, does that help make sense?
What's those like floaty things? Are those the metal?
Yeah, the reason they're floating things is because they're probably, like, remember the cross section is just one cut through the silicon. So those metal things are probably getting connected at a different depth, I guess, is, further into the display or further out of the display. So if you keep making cuts into the silicon, at some point you'll see these metal layers getting connected.
Oh, okay, yeah, that makes sense.
Yeah. So it's a little hard to see, but I'm hoping you guys kind of get a general idea. And hey, this is right up my alley. Actually, this is going to confuse the heck out of you guys. This is a good one. Well, so so you kind of can see, so like pretty much everything except the very, you see those real tiny, unfortunately I can't put markers on my display here, I don't think. This very bottom, those dots are your transistors. So that's like, I don't know, the bottom. So going up, so this, if you say this is a, okay, well, how should I describe this? Well, okay, so let's say going from the bottom, if you go up 1/10 of the picture, you'll see a bunch of small dots. Those are your transistors. Okay, so they're all on the surface of the silicon. Everything above that, those are all the different metal interconnections. So you also see how the metal lines are getting thicker the further they are from the surface of the chip. And it's just the way it works for various reasons. It's easier to do that. So the very top metal layers usually used for power supplies, clocking, those kind of things, because they're thick, you also can't make them very, you can't make their details very fine. So you do most of your routing, of signal routing, with the first 3, 4, 5 metal layers, and the bottom metal layers the top metal layers used for power and ground, just because they end up being thicker. Okay. Any questions about that, guys? I think once, okay, so let me do a segue here. So we have a problem this semester because what would normally happen is you guys would have access to the computer-aided design tools to do the drawings, or these, basically do a bunch of labs. so we would have a bunch of labs, and the first one would be doing these layouts. But those are, at the moment, those are only available on campus, and so we can't access them, and you can't do VPN or VNC or anything. So Dr. Olson and I are trying to find a way to around that so that we can provide you guys access, but I'm not sure we can. So some of the stuff we might just have to do on sort of on paper, which would be pretty lame. But just to kind of give you guys an idea, the real way to get a feel for it is you don't do a bunch of layouts and you get a feeling for what it means. But at the moment, we don't have that access off campus. But we'll see what happens. You know, I think a lot depends on, you know, we're trying to get the CAD tool guys and Cal Poly to do something. And anyway, so we'll see what happens. And hopefully in a week or two, we'll find out. Okay, so that was the segue. So, okay, so where were we? So, okay, so you have these top level drawings, right? We have all this stuff that we're drawing here and there. This is what we're drawing again. And so we're drawing, the upshot is, this is better. So this is kind of trying to say what I was saying is that, you know, in the CAD tool, you are doing a bunch of drawings on these different layers, and these different layers, let's say this is poly, is the manufacturing plant just takes that poly layer and makes a poly mask, and then they make a mask for the contact and a mask for the metal one, but from your drawings, okay? And because like any other manufacturing process, there are tolerances, there's like minimum size lines that they can build. Guys, give me 1 second. I think I have to go shut the blinds here so my dog doesn't see the neighbors walking around, so she stops barking. So give me 1 second. I'll be right back. All right. Gotta appreciate her enthusiasm. Okay, sorry guys. So yeah, so because you need to have an agreement. It's not really an agreement. The manufacturer just tells you this is what you have to do. It tells you the different sizes and spacings, etc. And those are called design rules, okay? And so let's see, what are these design rules? So here is the NMOS transistor. Like I mentioned, you draw first you draw an active, which is this green stuff. Then you draw poly, And then N select, you're telling it to make that active either N plus or P plus, and so on. But when you look at this, you also need to define certain sizes. For example, the length of the transistor, which is the distance between source and drain, is this guy here. So that's the length of your poly. And the width of your transistor, which is sort of going into the plane of the display, is W. Okay. And then you'll also need a substrate contact, okay, which would be a P plus to ground the substrate to help define it. Okay, and the PMOS is kind of the same thing, except you also need an N well if you have a single well process. And then you need to do a P select to make sure these are P plus implants. Okay, and together basically we have a, so this would be an NMOS, and this would be a PMOS. And then you'd have a bunch of metal contacts so here, like for example, the drain of the NMOS is connected to the gate of the PMOS, which is then connected to these two further top metal layers.
Professor,
Yeah.
could you explain what the N select and the P select does?
Sure. So what happens is, the overlap of N select with active creates N plus. The overlap of P select with active creates P plus. And the only reason is because that's the way the Foundry defines the layers, because they need to make both N plus and P plus, but they're both, so, okay, let me take a step back. So remember, the first place the active shows up, the active layer, active is a cut. So let's say we start with, so we have silicon, then we built a really thick silicon dioxide layer, which is our isolation, okay? So what we do is we put an active layer here and an active layer here, which what that does is it gives us a cut. I draw this right. Sorry guys, bear with me here. I'm trying to do this dynamically. So when I draw the actives there, it basically gets rid of this silicon dioxide wherever I have transistors, okay? But at this point, I haven't defined whether that's an N type or a P type, okay? Because remember, these are all happening in steps. So when I have an active mask, all I'm doing is I'm opening up a hole in that isolation, that silicon dioxide isolation. Okay. And so now when I want to build my transistors, I need to say, what I'd really like to happen is I would like my source, whoops. I'd really like source this to be n plus, and say this to be p plus, because I want this to be PMOS and I want this to be NMOS. So I need some way to define that, and that's N select layer and P select layer. So it's just saying, where do I do the implants for the N plus or the P plus? So how do I explain this further? So let me say this another way. So going through these steps, again, the active layer basically creates a hole in the, basically defines where there are active components, which are N MOSFETs and P MOSFETs, okay? Then the N select and P select are two different layers then that this determined if you are doing sort of, if whether you're getting an N MOSFET or a P MOSFET in those cuts. Does that make sense?
Yeah, that makes sense now. Thanks, Professor.
Sure. It's the thing is, yeah, because you have to build these devices up over a series of steps, and the Foundry sort of worked backwards from what they have to do to what layers you have to draw for them to be able to sort of put those on, do a step by step on top of each other to build your device. So it's not like inherently obvious. Okay, so any other questions, guys? Okay, so this is some description of the interconnection layers. Again, I think we've talked about this, that usually we don't have a poly 2. This is sort of a real old school, or actually maybe it's coming back. I don't know. Some processes have a poly 2, but typically there's only a single poly and there's multiple metals. And the way the numbering system works is that the lower the number is, the closer it is to the substrate. So metal 1 is the lowest metal, and metal whatever, this could go up to metal 9. We'll probably only work with metal 3 or metal 4, but the largest number metal is the one furthest from the substrate, closer. I mean, it's basically the top of our chip where you make contact to your package. And then if there are metal layers on the same, so if you had two metal 2 rectangles. So let's say if you had two metal 2 rectangles. So let's call this metal 2. You drew this in metal 2, and then you drew this in metal 2. Okay, those two rectangles will electrically short together because they're on the same layer. When the Foundry makes them, it'll make it like a cross. That's what it'll end up being. Okay, but if you do metal 2, and then you draw another rectangle in metal 3, although they're overlapping, those two don't short together because metal 3 is on a different layer than metal 2. It's going above it. And unless I draw a contact between them, they don't short together. Okay. So this is kind of saying the same thing is if you're looking from the top down, if you're, I don't know, this might be metal 1 or something. If you draw two metal lines, say this is metal one. These two don't connect to each other, again, looking from the top down, but if you cross them, like here, these two will short, okay? And then if you cross two different metal lines, they will not short unless you put a contact in between.
Professor, I'm a little confused.
Sure.
So in the cross photo you have at the bottom of the slide, is that like a top view or is that like a cross-sectional view?
They're both top views.
Oh, okay. That makes sense. Thank you.
So, okay. Okay, so these are different layers you have. So we talked about you might have 30 to 50 layers. So a whole bunch of those layers are the metal layers, depending on how many you have. Like I said, you could have nine of those masks would be metal layers, or 3 of them, or 4 of them. So those would be, those are the interconnection masks. Then you need to connect these different metal layers to other metal layers, or the metal layers you need to contact to the transistors. So there's a unique contact called contact. So this one's actually called contact, this layer. And this only connects metal 1 to either a source drain, be it N plus or P plus, or to a poly. So a contact is actually is a specific connection between metal 1 to your transistor, to either your gate of your transistor, source drain of your transistors, or some other, like say substrate contact. So I could have a contact here to this well, and that'd still be called a contact, and that's a specific layer. Okay. Then all the other interconnections between the metal layers are called vias. Okay, vias. So the connection between metal 1 to metal 2 would be called via 1. Okay, so if you had here in this cross drawing, if you had metal 2 on top of metal 1 in a cross, they wouldn't connect, but if you dropped in a via, they would connect. Okay, and notice this is a kind of a good drawing. Is, remember when I was sort of drawing the transistor, I had to draw, so this was my poly, I had to draw a bigger section of poly to contact to. So this was sort of the transistor. I had to sort of extend it out here. And this is, it's called a dog bone when you do that to poly, not here. But because the manufacturing plant can only make these in exactly a certain size, these vias or contacts, when you want to use them, you have to and then there's some uncertainty or process slack about how these things line up versus each other. So you need to overlap metal 1 and metal 2 around that via. So even if those layers move with respect to each other a little bit, you'll still get a good contact between them. Okay. And then, here is giving you some really good tips that because these vias and contacts have a significant amount of resistance. And so what resistance does in a CMOS process typically is it slows you down. You'll get a RC kind of, or if you have it on a power supply, it'll actually give you a voltage drop. But resistance is generally not a good thing in a CMOS process. So and then these contacts for chemical reasons have a high resistance relatively. So maybe a contact might have a resistance of 1 to 10 ohms, say, which doesn't seem very much, but like typical resistances of metals themselves are in the milliohms. So, this is like a significant additional resistance. So if you have space, you never want to leave, as you do these, drawing your circuits, etc., you'll end up with spaces here and there, and you want to use all, because you're paying for that silicon and all the area above it, you want to use it. So when you have connections and you have the room to do it, it's good to drop more than one via. So here, like you would, put in another via here, another via here, and cover it with more metal 2, and overlap it with more, I don't know what layer to use, more metal 1. So basically this guy and this guy connect to each other with lower resistance. And also contacts, because they're, it's getting, for various reasons, I think there's multiple reasons why vias, an individual via is a point of failure in the IC process, because they're sort of stacking these up in a three-dimensional way, the way the etching and all that stuff works. There's a possibility that your via will be an open, will not be a short. Now that possibility is very, very low that would happen. So the yield of an individual via might be 99.9999999% or whatever it is, very high probability. But remember, you'll have a billion transistors on your chip, and you might have like, I don't know, like 50 billion vias. So even a small probability of failure could mean that a via somewhere on your chip may fail. And if you use multiple vias, then if one fails, the other ones are still working. So it's always good to improve your yield. It's always good to drop in multiple vias. Okay, so when you do a CMOS inverter, this is kind of what it looks like. So I think I was drawing pieces of this anyway. So this is an NMOS down here. This is a PMOS. And notice that I have an active defined here. Okay, so this is the drain of the NMOS, source of the NMOS, and this is the poly gate. So this will be the length, and this will be the width of the transistor. Okay. And then I'm using this P plus. Remember, if I draw the cross section of this NMOS, it'll look like N plus poly gate. But then I need a substrate contact too, somewhere close to it. So that's this P plus here. Okay. And then I have the PMOS up here, which looks the same, except I have a P select instead of N select to make sure these are P pluses. And then my well, I have a well drawn also, N well. And then I have a well contact, N plus. Okay. Now, sometimes this is like really bad behavior, but it's okay for small distances. They're using the poly to get this connection between the gates. Poly has a very high resistance, but if it's pretty short distance that it needs to go, it's okay. So they're using a poly to connect these two. I never like that, but you can do it, and sometimes you have to. Okay, so this is everything before the metal lines. And then, any questions about that? About sort of the left half of the drawing? So we're looking at that inverter from the top, and we're looking at all the layers that were drawn to make that inverter. Okay, on the right side, okay, we're adding, we've got the same thing. Now we've added the basically metals and contacts. Okay, so we've dropped in metal 1. It looks like this. So it's this sort of this guy coming in here. And then we have 2 contacts. So remember we said the more contacts, more vias, the better. So these guys have dropped in 2. And then they've also extended out their poly. So it got kind of fattened up here because we need an overlap of the contacts. And the design rules tell you exactly what that overlap needs to be. Okay. And then we've also gotten some metal 1 here for this guy. Metal 1 here for this guy. And this metal 1 here for the output. And for each one, you've dropped a contact, 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 contact. So those are the contacts. Okay, everybody sort of see that? How, this is what you're drawing and simulating with from your point of view as a circuit designer. You're working with schematics, but you have to actually give this drawing to the factory to get an inverter. Everybody with me? Okay.
Yeah, we're with you.
Okay, great. So I love this. Design rules need to be obeyed. I love that. Do not violate design rules. I've seen it. I see it all the time. I don't know why people violate design rules, but the rules are the factory telling you what they can and what they cannot make. But what they're saying is what they can make. Let's put it that way. Even then, what they can make, you can remember going back to the economics of this thing. You are going to get a certain number of parts per wafer. Okay. Like this corner stuff, remember, the stuff gets wasted. So the number of die that you get it's called the gross die per wafer. Okay, so that's how many chips you get per wafer, and you pay for that wafer, right? Whatever it is, $3,000. You paid $3,000 for that wafer. You get those many parts, just geometrically speaking. But now you got to figure out how many of those parts are working parts. Okay, and as you can see, like that, like translates directly. The more of those parts are working parts, the lower the cost per part to you. Okay, and it's like a really bad curve and your yield drop. That's called the yield, is the ratio between the working parts to the gross die per wafer, or the total number of parts. Okay, so if the easier you make it for the factory to build your part, meaning that if you even if you give things more margin when you can, you'll improve your yield. For example, these are some different types of design rules, but one design rule is a minimum size. For example, there is a, let's say they have a layer, they'll say the minimum size needs to be this much. Let's say this is given in, say the minimum size is 1 micron, they told you. Okay, so that means like you can also not make it less than minimum 1 micron in any side. So you can make it longer, but you can't make it narrower than a micron. Now, if they tell you to make it the minimum 1 micron, and if you can, it behooves you to make the minimum wherever you can, like 1.2 micron. That will like significantly improve your yield. If you slacken, if you go do one better than the design rules by even a little bit, it really helps the yield. Okay, but anyway, the minimum size is one set of rules that you'll see. So for example, you'll see a section in the design rules for metal 1 or a section for metal 2. By the way, I put up a design rule set. I think it's just called a CMOS or something on the, maybe I'll open it up in a little bit. Let's just talk about this, and then it kind of gives you guys an idea. So one of them is minimum size. The other one is minimum separation. So what does a minimum size mean? It means that when they make the mask and they do the lithography, if you make something less than this minimum size, it may just not print on your chip, or some piece may not print somewhere and destroy your chip. Remember, you only need one defect to get a non-working chip, typically, unless you've built up redundancy yourself in the design. The minimum separation says, so let's say they've told you this distance needs to be 2 microns. So you cannot draw these things, 1 micron or something. This is so they can make sure these are electrically isolated from each other. So minimum separation, minimum size. Then there's a minimum overlap. For example, let's say this was a metal 1, and let's say this was poly. Okay, so what that means that I'm sorry, it's contact. So this is contact, for example. So let's say you had this contact, and this was your metal 1. So I'm drawing the cross section now. So this minimum overlap is this guy here. So this allows some level. So if, let's say, when they print, this ends up being a little bit further to the side. Okay, you'll still get a connection between these things. Okay. So those are the minimum sizes. Okay, so I think okay, so now let's see if I can jump over to sorry guys, I'm having noise issues again. Just give me one more second, please. Thanks. Sorry, guys. Um, okay, it's this guy here, a CMOS PDF. It's going to download for me. Okay, so these are like an example of design rules that we would have. Okay, um, so let me take a step back here about what this means. So every manufacturing plant has its own set of design rules. Okay, those design rules are given in units of length, like microns, nanometers. You know, the minimum size is given as 0.1 micron, or it's given as the exact size of a contact is given at 0.5 micron, or something like that. But for what happened is the one problem was introducing or using these fabrication plants for universities and research entities like Cal Poly or I don't know, JPL or something like that. So because the manufacturers don't really like to deal with people, the manufacturer is in the business of making and selling wafers. So the more wafers you buy from the manufacturer, the better a customer you are to them, and they spend all their time with you. If you are a student, or you're I don't know, if you're like a NASA, say, and you're only gonna make like 12 wafers of something ever and shoot them out into space, you are kind of low, not kind of, you're very low on the totem pole as far as the foundry is concerned. They'll still probably take your check and build you this thing, but it's just a pain in the butt to them. They don't really, doesn't move the needle for them. You know, they want to deal with Apple or Qualcomm or NVIDIA. These guys buy, 20,000 wafers per month or something, God knows what, right? So what happened is, but there's got to be a way to, but not there doesn't have to be a way, but people were trying to figure out what's a way to give access to these research facilities and so on to these foundries, so that the foundries wouldn't find it too annoying. So what they did was they created this entity. This was one of the entities in the US. It's called MOSES, which stands for something. It's actually part of USC. And then, there's a Euro practice in Europe or whatever. And these guys are kind of nonprofit brokers. So what they do is they get designs from all the different universities, and then they package them up for the foundry to use. So the foundry only deals with Moses, but maybe 500 different universities are giving designs to Moses, and these guys deal with the complexities. So what Moses did, and one is they created, because they have a bunch of different customers and a bunch of different foundries they support, they created this concept called the scalable design rule. Okay, the scalable CMOS, meaning that they made the design rules. Let me see if I can use an example. Actually, I think maybe I'll come back to this, but so what they did is they made the design rules a function of something called a lambda. Okay, so where is this explained well? So what they did was they said, okay, if I have I want to give the same design rule to people, whether I'm in a 0.18 micron TSMC process or I'm in a, I don't know, in a 65 nanometer TSMC process. How do I do that? Well, what they did was they made all the design rules. They took all the factory design rules and made a superset of the design rules that would work for all those, except it would have this multiplication factor called lambda. So for, let's say, 0.18 micron process, the lambda might be it might be 0.09 microns. Okay, for a 65 nanometer process, the lambda might be 35 nanometer. I'm sorry, guys, this will probably be more like lambda is 100 nanometer. So this 0.18 is really 180, just to make it easier for you guys to look at. Okay, so now what they said, okay, is that, say the gate, if you want to draw a gate of a transistor, it always has to be 2 lambda, the length of a gate. So your drawing is in lambdas. Let's say this was your gate. You make that always 2 lambda. And if this goes to get manufactured in a 180 nanometer process, it becomes 2 times 100 nanometer or 200 nanometers length. Or if it goes and gets fabbed in a 65 nanometer process, it goes that 2 times 35 nanometers is equal to 70 nanometers. But basically kind of gives this quote unquote sort of universal design rules or lambda based design rules. And so everything is a function of how many lambdas you draw something, and depending on where it goes to, the lambda is different. So for example, where do they have that? These design rules, the same document, okay, is supporting a 0.5 micron process from onsemi, a 0.35 micron process from TSMC, or a 0.18 micron process from TSMC, and so on. So, and then there's a list of processes that it's compatible with, okay? And given that we are a university, we end up sort of designing in lambdas typically. So that's why there are these lambda design rules. When you go to, you might still see these lambda design rules if you go work at a place like JPL or someplace like that where you're designing chips, or you go to grad school or something. But at a company, you don't really see these lambda rules. But anyway, it's just conceptually, it's the same set of rules, but they're given in lambdas. So let's say if I jump around to where's a good place? Active. Okay, so basically active minimum. So remember we talked about the rules for minimum size, minimum spacing, and like overlap, right? So here we have a minimum width, which is 3 lambda. And that could mean different things, whether you're in 180 nanometer, you're doing a 180 nanometer design, or a 65 nanometer design. Okay, but it's given in lambdas, so it'd be the same for everyone. And then you have minimum spacing. You have that's minimum spacing between two actives. There's a minimum spacing between source and drain active to a well edge, or a source substrate contact to well edge. So these are all spacings. 2.2 through 2.5 are all minimum spacings, but they're spacings between different the same layer but doing different things, okay? Or this layer to another layer. So for example, 2.3 is spacing from the active to the well edge. Okay, does this all make sense? I know it's like a couple of hard to describe. So so the real design rules are the so-called native design rules, and those are all always given as sort of actual distance, right? That's given at 65 nanometer or 35 nanometer or whatever. These lambda rules are these attempt to do the design that you can fab it in a bunch of different processes. And those are the rules we'll be using. So here's some examples, like, so the minimum sizes for poly, what example is defined as 2 lambda. So the minimum width of a poly in a 180 nanometer process would be 200 nanometer, and a 65 nanometer process would be 70 nanometers. Now notice an interesting thing. If you use the native design rules, your minimum poly width could go as low as 180 nanometer or 65 nanometers for a 65 nanometer process. So this is already an inefficiency, but because they wanted it to multiply it by the same multiplication constant, it gives you this inefficiency in sizing. Okay, so anyway, poly is 2 lambda minimum width, metal 1 through metal 3 is 3 lambda spacing. You know, so regardless of if you're in a 65 nanometer, 180 nanometer lambda based rule, the separation is always 3 lambda for poly, and also 3 lambda for the metal layers. Okay, now the end wells, or the wells, because it's a diffusion, it's much coarser spacing and sizes. So the end wells are 12 lambda minimum size, 18 lambda separation. And you don't have to memorize these. I mean, these are in that document, the CMOS design rules. So when you're doing your design, the first couple hours of your design, you keep referring back to the design rules, but there just seems to be, there's a lot of design rules, but there's really not that many. And pretty soon you kind of remember what they are. So anyway, it's not so bad. As you do layout, you get kind of more and more comfortable, and you don't have to look up the rules anymore after a little bit. So this is, so remember we said there is minimum size, spacing, and there is minimum overlap. So for example, if you have a poly, metal 1, and contact, the poly and the metal 1 need to overlap the contact by a minimum size. So the contact is always going to be an exact 2 lambda size, and it's always going to be a square. The contact is always going to be square with 2 lambda on each size. And the via is also always, any vias, via 1 through X, are all also going to be square with 2 lambda minimum size. And then you have this minimum overlap of 1 micron around it, which makes the size of the metal 1 or metal 2 around the via 4 lambda, because you have the 2 lambda of the via and then 1 lambda, extra lambda on each side, okay? And then the poly, it needs to extend out over the transistor. So this is the length. Remember this, this is the transistor length here. This is the transistor width. So this is length, this is width. But then you have to extend this out further, again, because you have some slack. The fab wants to be able to move this poly to the left or right a little bit on top of the active, or give themselves that slack without causing a problem. So that gives you this minimum overlap there as well. Okay, and then you have minimum sizes for the transistors. And there's like different sets of rules. There's a CMOS sub M design rules, which is even, which is sort of stands for sub micron, just different set of rules, which gives you different multiplication of those things. And this is an example from that same document that I showed you. What is this? This is for well sizing. So it's got the minimum size and then minimum spaces between the wells. Now notice this is interesting. Wells at different potentials need to be further away from each other than wells at the same potential, because their depletion regions might end up shorting still. Boy, I'm gonna forego these fingers because I think these are ways of improving the efficiency of your layout. And I'll come back to this later. I think it might not make much sense right now. And then stick diagrams. You know, again, this is a kind of a university thing to use stick diagrams. So stick diagrams are a way of, it's just to hand draw the rough layout of your design without having to worry about the sizes. So it's a sort of a quick hand drawing of your, so this was like, say, you got a complex schematic, which would give you a complex layout. But as a first step, you kind of do a quick connectivity drawing without worrying about the sizes and so on. So you got a feel for the layout. But honestly, outside the university and outside these books, I've never seen a stick diagram used. So I just want to mention it, but I don't encourage you guys to use this. I've never seen it used. Okay, so those are all the ideas behind the design rules, guys. Any questions? No, it can get a lot confusing about what we're talking about until you actually start using the computer-aided design tools and doing a layout. And I hope we can get that online in a couple of weeks. But in the meanwhile, the idea is that as the designer, you actually have to translate your schematics to this thing called a layout, which is a top view representation of all the mask layers. And that is what you send to the Foundry to build your chip, okay? And then the second idea is that there are these design rules that tell you exactly how you have to do those drawings for them to be manufacturable by the Foundry. Any questions, guys?
Nope.
No
questions.
Okay, guys. Well, have a great long weekend, and I'll talk to you guys on Tuesday.
Have a
You
good
too,
weekend,
Professor.
Professor.
Have a
Take
good
care.
one.
Thanks.
Thank you,
Bye.
Professor.
Thank you.